R&D, our demonstration reactor. That reactor is the birthplace of the SAS reactor, the iron-based study phase reactor, as well as the cobalt-based study phase reactor. So 1 meter internal diameter and it's about 35 meters high. The 5 meter internal diameter study phase reactor operating with iron catalyst at this stage. That was a SAS reactor to start with. In conclusion, we were successful in developing new generation FT reactors, both for low temperature and high temperature. The SAS reactor for high temperature and the study phase for low temperature. It resulted in a significant, and if I say significant, it is really now that the capital cost of the FT section is now more or less similar to that of the refining section. If I really mentioned the value of this demonstration reactor, we used to verify our models, we use that to develop the reactor internals, so we remove the uncertainty with regards to mechanical design of reactor internals. We have a successful history of scale-up, and we will continue to be successful in the future. And there will be no mechanical risk for a large-scale slurry phase reactor, because we have built those big monsters at Secunda at 22,000 barrels per day. The reactor internals are very similar to those as well. So there are no mechanical risks to design and build those reactors. I thank you.
Thank you very much, Anton.
Dave King was chosen as our visiting expert for reasons that you'll see once he gives his talk. He's one of the experts in the area of surface sciences related to catalysis, and had been working in this area for many, many years. Dave King's background is that he was born in South Africa, got his first degrees at Wits University of Witwatersrand in Johannesburg, left in the early 60s to go to the UK. As he says, and I know he had to leave during those sort of political days, and it was South Africa's loss and England's gain. He went to England, and his career just blossomed while in the UK. He went first to East Anglia, University of East Anglia, and from there he went on to Liverpool, where he became eventually chair of physical, took on the chair of physical chemistry. He overlapped with Graham Hutchings, who many of you know, and as Graham was arriving, so Dave was on his way to University of Cambridge. At the University of Cambridge, he worked his way through from chair of physical chemistry to head of department, and he's got to give up the head of the chair of chemistry at the moment at Cambridge, because his new position is, is Chief Scientific Advisor to His Majesty's Government and Head of the Office of Science and Technology. So his new position now is that of Scientific Advisor to the UK Government. So we hope in this role he'll influence decisions that they make to chemistry in the years ahead. And that's his position at present. And he's now moving, so he'll spend most of his time, I think, in London, some of his time in Cambridge. We hope he doesn't lose contact with the chemistry community. As he defines his area, I'll just read it to you. The objects of our work are to provide a detailed understanding at a molecular level of the relationship between surface structure and molecular reactivity, focusing on catalysis. From the understanding developed in this way, new approaches are being developed to control the rates and selectivity of catalytic reactions. Dave, I'm going to let you give your title to your talk. It relates to this topic, surface science and its relationship to catalysis.
Thank you very much for those kind words, and I feel greatly honoured, of course, to be here, and also at the same time a bit of an interloper, because I realise that in terms of science and technology I bring a slightly different slant to the meeting from what you've been hearing. In fact, this is not my particular group of people that I generally move with. I'm a chemical physicist and a surface scientist, and we are a rather separate bunch of communities. The more we can communicate across those barriers, the better. So I'm absolutely delighted to have this opportunity to be here. what I'm going to talk about is the work that we've been doing on methane partial dissociation in particular. So the focus of the work was really on the question, from a chemical dynamics point of view, how does methane dissociate on collision with a metal surface? That's the essential question. And we then went on to look at the reaction between methane and oxygen to see if, under our conditions, we could get the reaction to produce the products that you chaps like to have and call syngas. You don't do this sort of work without a team, and this is my team, and in response to the comment that was just made, it will continue to be my team in my new role. I will continue as a research professor at Cambridge. Down in the front is Melissa Peterson from Cape Town, who joined me as a PhD student, and Melissa has done some of the work I'll be talking about. And up here is David Watson. He's done a lot of the work I'll be talking about, and the others have contributed rather generally to this. Amy Walker, in particular, I'll be talking about her work in the early part of this talk. Now, let me just very quickly say that we've been involved, as Neil said, in technique development. One of the techniques that we developed was single crystal adsorption calorimetry, and I just show this to give you the flavor of where we're going at the moment. The idea of this experiment is to measure directly the heat released when a bunch of molecules hits a surface, and when those molecules go into a final state that is well defined. Right? So the final state, for example, if we had ethylene molecules, we might choose a system where we know spectroscopically that the final state is ethylidyne. And then we measure the heat released in forming that species, and so we can then get back the bond energies. And so what we're trying to do using this system that we first published in 1990 is to set up a bond energy database relevant to surfaces. And the first part of that database has been published in 1998, and we're continuing to gather data on an extensive range of systems. Let me just give you one other example of the sort of work that we're doing, and I'm not going to refer further to in this talk, and that is the stunning capability of scanning tunneling microscopy. So here is a recent picture, unpublished as yet, of an ethylene molecule. That white blob is a single ethylene molecule sitting on a silver 111 surface. So each of these blobs here represents a silver atom in the surface. You can quickly see that that's got a hexagonal structure. And by triangulation, you can also quickly see that the ethylene is sitting on top sites of the silver atom below. But what was more interesting is when we put several more ethylene molecules on the surface, and you start nucleating a well-defined structure. And as you do that, here we've got 3 molecules sitting on that surface. You can immediately see the rings of bright and dark area around that 3-molecule cluster. Now, these are what are called Friedel oscillations. This is the first time Friedel oscillations have been observed in the way that we demonstrate here, that we are stereoelectronically directing molecules into positions on the surface. If you look at this picture, you can see 3 silver atoms here that are brighter than the rest, and the next 3 ethylene molecules you put on the surface go into those positions. So if we just put 3 more ethylene molecules on there, the ethylene molecules go onto the silver atoms that have the highest charge density at the Fermi level. And so here we've got a 6-molecule cluster. And as you build that up, you form a structure that is called a 2x2 structure. You can see already the incipient 2x2 structure. That structure is built up through the interference of these Friedel oscillations, these electron charge waves, and that interference pattern producing bright and dark areas. Right, so being able to look at these things on surfaces with that sort of resolution is what we're all about. And in this particular talk, I'm just going to focus on this one reaction, methane partial oxidation, but much of what I will say is what our focus has been on, which is the methane dissociation step. So, very brief introduction. Methane dissociation I will talk about the products on the surface, the stable products on the surface of the methane dissociation, show that we can get deuterium exchange with those products, and then that we can react those products either with oxygen or continuously between methane and oxygen. So that's the outline of the talk. And the technique here, for most of what I'm going to say, is supersonic molecular beams. So we follow catalytic reactions at a single crystal surface here, so that the surface is totally well defined, and it's followed by beaming two reactants at the surface using two molecular beam sources. So beam source 1, beam source 2, where we can state control the incoming molecules. So we can send them in, as you will see, this is critically important, with a well-defined translational, vibrational, and rotational energy. And we can then see what is critically important in the dissociation of the molecule. Perhaps I should just say that in terms of molecular beams, there are some very, very distinct advantages in using them. One of them is that we can obtain the so-called sticking probability, the probability that the molecule dissociates on a single collision, with enormous accuracy. And so a lot of what I'm going to be showing you is measurements of these sticking probabilities. We can control, as I've indicated here, the state of the incoming molecule. We can, under difficulty, control the orientation of the molecule at impact. That's true for certain molecules. What we cannot control is the point of impact within the unit cell on the surface. So what we always have to remember is that we're always looking at the average of collisions with the surface over the entire unit cell range. So by this I mean that the molecule could hit the fourfold site, the bridge site, or the ATOP site, or anything in between. So we're always integrating over all of those collisions. That's what's out of control, and so is the phonon population. In other words, we still have a temperature rather than a phonon population. This is the surface I'm going to be talking about, the platinum 110 surface, chosen for this study precisely because we have a range of different coordinations of metal atoms at the surface, and because we also know the structure of this surface in fine detail. And under most of the conditions that I will be describing, this surface is essentially unrestructured. It retains this hill and valley structure indicated here during all of the processes I will describe except one. So surface restructuring has always been an important part of our work. Okay, so what I said was we're state controlling, just to indicate how do we state control the incoming methane. We can seed the methane in helium, argon, krypton in order to alter its translational energy without altering its internal energy, and we can vary the nozzle temperature, the source temperature, which then alters both translational and internal energy. By playing with the seeding and the nozzle temperature, you then can get everything under control. You note at the bottom here, and I'm going to come back to this because this turns out to be a critically important point, that in a supersonic beam, the rotational temperature is cooled to the lowest rotational levels being occupied only. Now this turns out to have been critically important, but we didn't realize this in the first phase of our work. So now, methane dissociation on collision with the surface, the sticking probability as a function of translational energy at constant rotational and vibrational energy. It's shown here, and I don't think that this result should surprise anybody here. So what we're doing is increasing the speed with which a methane hits the surface, and when we get to 200 millivolts, or about 20 kilojoules per mole, or about 5 kilocalories per mole, depending on which energy you work in. At about 200 millivolts, you'll see the sticking probability rises dramatically. So we're now flying the molecule over the activation energy barrier, and we're measuring that barrier with some accuracy. The incoming beam, even supersonically, is not monochromatic. So what you can see is the energy distribution here of the incoming beam is what is determining the sharpness of this line. So it's a remarkably sharp activation energy barrier. Remembering that we're integrating over collisions around the surface, which means, I believe, that there is one particular collision parameter with the surface that leads to this relatively low activation barrier. So this is the dissociation energy for a given vibrational and rotational energy content for the molecule striking the surface. So here's the schematic, and ignore the one here, but look at the two. The schematic of what I'm saying in terms of a simple potential energy curve. Methane comes in, weakly absorbed on the surface, and if I fly it in with enough energy, I can get over this barrier into the dissociated state where one hydrogen atom is ripped off the methane during the collision process. Okay, so we have clarified that activation barrier, and as I say, nothing much is new there. If you look at the literature going way back, activation energies have been determined in the range from 5 to 12 kilocalories per mole, depending on the metal. Now came the surprise. If we plot this up on a logarithmic plot, and Amy Walker collected this data, and I'd like to pay a tribute to her, each of these data points takes an enormous amount of energy and time to obtain. So she collected a good body of data, and each curve here, if we just take these two full curves as the extrema, each curve corresponds to a given vibrational content of the molecule. So you'll see, first of all, that vibrational energy is very important. So this is the lowest vibrational energy down here. This is higher vibrational energy. You've got many orders of magnitude increase in the dissociation probability as you increase the vibrational content of the molecule, but also, of course, translational energy. Now, this is a logarithmic plot, so the barrier that I was talking about before is this climb in the signal bit here. That's the activating process. But what we got excited about was the fact that as we slowed the molecules down, the dissociation probability was going up. So getting excited about that was simply, here was a process that gets much, much faster as we lower the temperature of the incoming molecule. And when I say lower, here we're doing something called anti-seeding. So we're deliberately slowing the molecules down by putting them in a rare gas mixture where the rare gas is much heavier than the methane molecule. So the methane is slowed right down to something like 15, 20 millivolts at the slowest. And the sticking probability is climbing, and you'll see that we're climbing up to the point where the sticking probability is becoming close to the value for the very high energy process. So we've got a second process here, which only occurs as we slow the molecule down. Now, both of these processes, as you can very clearly see here, are facilitated by increasing the vibrational energy content of the molecule. So as I increase the vibrational energy content here, I speed this up, and here I speed it up considerably more. We analyzed the form of vibration that is involved, and I don't plan to take you through this, but it's a simple Boltzmann type analysis of the data. And I know I shouldn't flash the graphs up quickly, but I don't want to spend too much time on this. The analysis is relatively straightforward. And here's process number one occurring at low translational energies. These are the very slow molecules. And here we see that the vibrational energy involved is about 1430 wave numbers, which is the deformation modes of the methane molecule. Whereas when we come up to the activated adsorption process, you'll see it's around 2,400 to 3,000 wave numbers, which is actually close to the CH stretching modes. So we're saying that in the low translational energy process, it's these deformation modes that are involved, and it's tempting to say that the deformation, only tempting though I have no concept of information about this, the deformation involves the hydrogen moving away from the carbon atom, exposing the carbon during the collision, and you could then get direct orbital overlap between the metal and the carbon. Whereas in the high translational energy activated process, what we have is orbital overlap directly with the hydrogen atom. So as we stretch the hydrogen away from the methane, it can bond to the metal, and we then break the hydrogen-methyl bond. It's facilitated. Now we can't distinguish between these modes and these modes. All we know is it's a stretch and a deformation which is involved. Now we reach an important conclusion about that low translational energy process, because there seemed to us to be one of two possibilities. One is that low translational energy process is one which is precursor mediated, which means that the molecule coming into the surface is trapped into a weak, maybe fizzy-sorbed well, for long enough time that it then finds itself over into the dissociated state. Or the alternative is that we have a direct steering-assisted process. This is a process we first discovered in hydrogen adsorption on platinum 100. So the steering-assisted process, imagine that I send a molecule into the surface, and there is a zero activation energy process, but that process is entropically inhibited, so that it's very difficult to find your way around this potential energy surface into that valley that leads to that process. So if I send the molecule in very quickly, it just slams up the other side of the valley and has to go right over the activated barrier. If I slow the molecule down, it can steer itself round until it finds itself through this zero activation barrier process. So that's the steering process. And because vibrational energy matters in that process, it means I haven't trapped the molecule, and it means I have got a steering-assisted process. So slowing the molecule down is facilitating the steering-assisted finding a way through to this valley into the dissociated state. Okay, so here's the summary there. For the methane dissociation, we've got two direct dissociation processes. One is the normal activated process that I think you're all familiar with, and the other is this new steering-assisted process that only occurs when the molecule is slowed right down on impact with the surface. And this is the vibrational excitation, and finally, I haven't mentioned this, but the rate does increase with increasing surface temperature. So again, that's something you would be familiar with. Either surface temperature or the translation energy of the molecule will assist you in getting over the barrier for the activated process, and the Boltzmann energy from each of those terms is equivalent, absolutely equivalent. Now comes the difficult bit. Having said that we can slow this down in a molecular beam, we slow it down to 15 millivolts. Well, 15 millivolts isn't very different from room temperature. So instead of using a supersonic beam, we did the obvious thing, which was simply to fill the chamber with methane at room temperature to measure the sticking probability. And when we did that, we found that the sticking probability was unbelievably low. So under a condition where our experiment with the supersonic beam predicted a sticking probability of 2 times 10 to the minus 4, and we should have got a large carbon buildup on the surface, instead we find the sticking probability is immeasurably low. So it was below 10 to the minus 5, 10 to the minus 6. So we had two choices at that point. Was the supersonic beam experiment due to the fact that we were seeding or anti-seeding the beam with heavy rare gas atoms, krypton? For example, could the molecule be adsorbed in a fizzy-sorbed state for a short time, and while it's adsorbed there, receive a collision from the krypton atom, which could then cause the breaking of the bond? Now we tried that. We just sent in a highly energetic krypton beam, and we got no dissociation under that condition. The other possibility is that actually this process is inhibited by rotational energy. At room temperature, thermalized molecules have a high rotational energy content. In our supersonic beam, we've frozen out the rotational modes. So it could be that the sticking is inhibited by these rotational modes, and that's why you don't see this non-activated process in the normal run of events. So we can test that in our system, because as you reduce the flux in the supersonic beam, it switches from being supersonic to thermal. So this all depends on flow within the supersonic source. So you simply reduce the methane flux and up goes your rotational energy. And when we do that, we find that there is a decrease in the sticking probability, and that decrease is directly associated with the rotational energy content of the methane molecule. So, not wishing to go into detail on that, but it's certainly of interest in terms of dynamics. I just stress this one point. If we come back to that activated process, so here's again my logarithmic plot of the rate of dissociation of the methane molecule as a function of translational energy. You'll see that as I increase the translational energy, I see this activation barrier here, but then change the nozzle temperature, and this does cause some increase in the rotational energy content. You'll see that I shift the barrier upwards. I shift the barrier upwards substantially, 70 millivolts upwards. Right? So what this means is that if I rotate the molecule fast, what is needed is a higher translation energy to get over the barrier for this dissociation. And so we conclude from this that we have rotational quenching of the methane dissociative absorption. So as I increase that rotational motion, if the molecule starts dissociating, as it is here, but it's rotating, then I can just rip the hydrogen metal bond off, and so the faster it rotates, the slower is that dissociation process. Now we're just working on a theoretical model to describe that process, and we haven't got there yet. So let me now switch to a separate part of our problem. This was the end of Amy Walker's work, and we then proceeded to look at the coverage dependence of this rate of dissociation, and we found an unexpected result. So as here's a nice linear plot, it's a bit easier to follow, the sticking probability as a function of coverage, and this now depends critically on the surface temperature. You'll see that at 370 and 400 Kelvin, the sticking probability tends to saturate at quite a low coverage. We now know exactly what that coverage is. It is about half a monolayer, so we can take this arbitrary out. Whereas if we absorb at a higher temperature, we find that the sticking probability, again, very consistent, but now saturates at something like twice that coverage. So the question is, what is happening here? The initial sticking probability, you'll see, increases with surface temperature, which is related to the activated process I've been describing. So this part of the curve is not surprising. It's the fact that it saturates at such different coverages over the narrow temperature range difference from 400 to 500 Kelvin. So the question is, what is happening over that range? And it turns out that this is what we would call a species effect. So the next step was to determine what is the dissociation product on the surface. So the methane molecule strikes the surface. At 180 degrees Kelvin, it's very easy to see what the product is, because the umbrella mode of the methyl group is very easily seen in infrared spectroscopy. When you heat this up, you'll see that there's a good amount of hydrogen desorbing. So this is the hydrogen partial pressure shown here. This hydrogen desorption is the desorption from the species that is decomposing as we heat up from 180 to about 350 Kelvin. If you keep heating up, you'll see that there is another peak here, and this is the species that is the hydrogen that is left attached to the carbon atoms on the surface. And simply by determining the ratio of these peaked areas, we find that this species is CH. In other words, the ratio of hydrogen to carbon is 1 to 1. So what we're left with is the CH species. Now, density function theory calculations show as well the most stable product of methane dissociation is CH. So CH3 and CH2 are metastable with respect to CH. CH is more stable than carbon on the surface. It's more stable energetically than carbon. So why does the hydrogen come off here and leave carbon? Because the hydrogen is going to form H2 in the gas phase. So that last step is entropically driven, not energetically driven. Okay, so we've determined that the dissociation product at around, sorry, let's stay with this, at around 370 Kelvin is CH. Then if we have a surface temperature above 500 Kelvin, we're left with C on the surface. And it's this temperature range over which that coverage dependence of the Stigma-T change. So we see that if we adsorb at 500 Kelvin or higher, the product on the surface is carbon, and you get much more carbon on the surface, twice as much. Whereas if you adsorb at this temperature here, the product on the surface is CH, and you end up with half a monomer on the surface. The CH molecules stay apart, and the carbon tends to congregate into clusters on the surface. And this happens until you saturate the surface. So if we just adsorb at 370 Kelvin, we find that it remains as CH throughout the adsorption range. There's no change in the product species on the surface until the surface has half a monomer of CH, at which point we have an ordered structure. So ordered structures are what we often observe in adsorption on single crystal surfaces. All right, just to summarize, because I'm not going to go into this in any detail, the product on the surface is CH. If you adsorb at 370 Kelvin, if you adsorb above 500, the product is carbon. And we do see some coupling, but that is only under the condition where we're beaming methane at quite high fluxes into the surface at 500 Kelvin, and we see some coupling into a CCH species. You see an ordered overlayer at 370 Kelvin, and the methane dissociation is effectively blocked by these CH species on the surface, which is why the Stigma-T drops quickly on that surface. Now this curve is not going to tell you very much. It's the next view graph that's going to hopefully give you some information. So we're now going to examine the reactive properties of this CH species. So here you see we're absorbing deuterium onto a clean surface by beaming a deuterium beam at the surface. Now, in our apparatus, we first of all fire the beam at an inert surface, and then we remove the inert surface and let the beam hit the reactive surface. And the point at which it hits the reactive surface, is here, and at this temperature, the deuterium is reversibly adsorbed. So the adsorption takes place, but desorption occurs as well, and so the process is saturated very quickly, and if we stop the beam by putting the inert surface in the way again, you see the deuterium is rapidly desorbed. So we have an equilibrium between gas phase and surface species, and this is just to show you that at this temperature, what remains on the surface in vacuum is effectively nothing. It's a clean surface. Now we fire a deuterium beam under exactly the same conditions at a surface which is pre-adsorbed with CH. And you'll see that when we do that, the curve looks totally different. So now there's a distinct uptake of deuterium. But if we look at the bottom part of this curve, you see what's happening is that we're initially seeing a pulse of hydrogen and then a pulse of HD. And what we're looking at is the facile exchange of the CH with deuterium to form CD. Now that exchange process is extremely fast. You can see that as we impinge that beam, within seconds the exchange process is over. So as fast as the molecules dissociatively adsorb on the surface, they exchange with the CH, and you end up with the CD species. So by the time the H2 comes off first, because the CH is exchanging rapidly with the deuterium and putting hydrogen atoms onto the surface, which then desorb, and then the HD. By this time, we're left with fully exchanged CD on the surface. So that exchange process is facile, and we've looked at the kinetics and dynamics of that process in some detail. I don't want to go into this in boring detail with you, but essentially, if you can see from the back there, the chemical equations indicated here are the essential ones. The CD and hydrogen atoms are in equilibrium with the CHD species, the CH2 equivalent, and it's simply this process that is leading to the exchange. Very fast process on the surface. So we can set this up as a system of coupled differential equations, and the interesting question was, how does this process occur, and is it facilitated by tunneling through a barrier? Wherever hydrogen atoms are seen in the literature, you'll find the question of tunneling, and what we can show you, this is simply a best fit from the coupled differential equation approach to our data using one variable parameter, and that's the rate constant for the forward and backward reactions of the exchange of hydrogen and deuterium. And the reason I'm showing you this is simply that if we look at the 0 point energy and feed in the partition functions for the exchange process in the two directions, you find that you get a factor of 2.6. So in other words, we believe that what you're looking at is not related to quantum mechanical tunneling of the hydrogen atoms at all. It's quantitatively explained in terms of the 0 point energy difference between the CHD and the CDH species, the CH plus D and the CD plus H species on the surface. Now, perhaps of more interest to you is the fact that if, and perhaps you won't be surprised, that if we now increase the deuterium flux at 370 Kelvin, we can clean all of the CH species off the surface as the deuterated products equivalent to methane. So here you'll see that as soon as we switch on the beam, off comes CD3H, and then as the CD3H is consumed, so we get CD4. The ant is showing away. All right, so once again, once the exchange is complete, then the only product is going to be the CD4 product. And this just indicates that at the end of that process, when we examine the surface for carbon presence, which we do just by beaming oxygen at high temperatures, quantitatively reacted off, you'll see that there's very little carbon species left on the surface. So this is after the exchange with, the reaction with deuterium. So we're just pushing the process by increasing the deuterium flux all the way back to methane. So the process is reversible. If, however, you took the step of heating up to form carbon on the surface, and then try this, you never get one bit of methane off. So once you've dissociated the CH to carbon, then the reaction is no longer facile. Something irreversible has happened on forming carbon on the surface, and we can't then push the reaction back to forming the methane products. Okay. Where have we got to now? We've seen that CH is a stable product in this absorption range. CH forms this ordered structure. The exchange with deuterium is much faster than the other way around, but this is just due to a 0 point energy difference. We can completely rehydrogenate CH to methane, so we can reverse the process. And now we're going to look at the oxidation process. What we find is that this CH species is much more reactive to oxygen than the carbon species that's formed at higher temperatures. So let me just summarize quickly the carbon oxidation data. If we go back in the literature, we find something quite interesting. That if you put carbon on a metal surface such as rhodium or platinum, and then introduce oxygen to the surface, the carbon monoxide that is produced is vibrationally hot. So the carbon monoxide comes off with energy levels up to n equals 7 occupied. This was shown by laser interrogation of the desorbing molecules. So vibrationally hot, what is the translational energy of those CO molecules, and do we see the same thing in our work? So now we take a look at what happens. So this is pre-adsorbed carbon formed above 500 Kelvin on the surface, and we then beam in an oxygen beam, and very quickly up goes the CO signal, and then after that comes the CO2 signal. We always see a CO pulse first, followed by a CO2 pulse. That's exactly what you would expect. The carbon monoxide needs to be formed first because the reaction to produce carbon dioxide is this reaction, sequential reaction of CO picking up a second oxygen atom to go to CO2. So when we're beaming the oxygen at the surface, the carbon monoxide formed has a lifetime on the surface, and during that time, if it picks up another oxygen atom, it comes off as CO. And the probability of that process depends on the coverage of adsorbed CO, which builds up with time along this time axis. So we can model that very easily using a Langmuir-Hinshelwood approach. And so can we model the product ratio of CO against CO2. So as we raise the temperature, we see that the percentage of CO2 produced goes down, so that the percentage produced at 450 Kelvin is close to 100% CO2. And then as we raise the temperature to about 650, 700 Kelvin, you see that the product has switched to carbon monoxide. Now, in the Langmuir-Hinshelwood approach, this is because of the lifetime of the CO on the surface getting shorter and shorter, so the time scale it has to pick up oxygen atoms gets shorter and shorter. So that looks very clear. However, remember that under certain conditions, we said that the vibrational energy content of the CO molecule that is formed is high. Let's skip that. And then we look at this curve. This is a high time resolution curve showing that pulse of carbon monoxide formed at a relatively high temperature. So this is at 650 Kelvin. So here you see that within the time resolution of our instrumentation, as soon as the oxygen molecules hit the surface, the carbon monoxide is coming off. This is what we call an impulsive process. It doesn't appear as if the carbon monoxide has a significant lifetime on the surface. Now, it looks as if, therefore, it's a kind of Ely-Reveal mechanism rather than a Langmuir-Hinshelwood, but it doesn't have that characteristic either, because you'll see that after this sudden rise, there is a gradual increase that fits in with the Langmuir-Hinshelwood behavior, and then as the species on the surface, the pre-adsorbed carbon is consumed, the rate goes down. It seems to follow Langmuir-Hinshelwood as well. So there is actually an apparent mixture of processes occurring here. When we analyze this a bit further, it becomes a lot clearer. Now what you're looking at is rather a nice curve. We're looking at the angular distribution of the carbon monoxide desorbing from the surface. So if this was a trapped carbon monoxide molecule, the angular distributions should be what we call a cosine law distribution, which is this little contribution down here. So some of the molecules are coming off having fully trapped their excess energy onto the surface. But most of them are coming off, shooting off at a particular angle to the surface. So the molecules are shooting off at about 30 degrees from the surface normal. We've got a pair of rabbit's ears. Now, the reason for that is very simple. I don't know if this superimposition works. Those carbon monoxide molecules are formed on these parts of the surface here. So the surface is kind of faceted. The carbon, we know, is bonded to these facets on this side, and the carbon monoxide is impulsively desorbed from the position the carbon atom had as the oxygen adds onto it. And so the carbon monoxide is coming off in that direction, and of course in the orthogonal direction here. We can do an analysis of that, and we can also measure the translational energy, and it turns out that the excess translational energy of those molecules is about 135 kilojoules per mole. Now, if I translate that into a temperature, these molecules are emerging from the surface with a temperature of 11,000 degrees Kelvin. So when you produce carbon monoxide from a metal surface, you're producing extremely hot, translationally hot carbon monoxide, and you've got to think about what happens on the next collision. In our apparatus, we never look at second collisions. We only have one collision with the surface. Okay, so it's very translationally hot, and remember I said vibrational levels up to n = 7 are occupied as well. This fits in precisely with my statement that these molecules are coming off with a high temperature, about 11,000 degrees Kelvin. How can they do that? Well, this is back to our calorimeter, and from the calorimeter we have a series of bond energies, and just using that bond energy database, the only process that we could find that would produce this excess energy in the carbon monoxide molecule is the process indicated here, where a carbon atom reacts with an incoming O2 molecule. Right? So the key step is this one up here, where the carbon reacts with a chemisorb, or I mean it's more likely chemisorb dioxygen molecule before it has dissociated, forming this activating complex. That activating complex, when it decomposes, forms this adsorbed carbon monoxide. We now have the excess energy as the carbon monoxide emerges that we're measuring experimentally. So we're falling down this potential energy surface here, and out comes the carbon monoxide extremely hot. As the surface temperature is dropped, so the carbon monoxide molecule finds that its energy, excess energy, is trapped in this quite deep well here. This well is a good 130, 150 kilojoules per mole deep. So it's quite a big well. And as we drop the temperature below about 600 Kelvin, more and more carbon monoxide molecules are trapped in here, and so they become thermalized to the surface. And so we get this mixture of events happening. We get a mixture of this prompt CO desorbing and the thermalized CO, which can then undergo reaction with oxygen atoms to form carbon dioxide. Okay. So just to summarize now, we see that carbon monoxide is the favored product at high temperatures. The hot carbon monoxide is produced when the surface temperature is very high, and this is a misprint. That should be O2C intermediate, not O2CO intermediate. And at lower temperatures, when we have CH present as the dissociation product of methane, then we get the reaction to go much more quickly through CH. But when the CH reacts, we find that the product is always carbon dioxide. We don't form carbon monoxide from CH. We haven't been able to observe it in carbon monoxide from CH. So let me just show you the reaction pulses with CH. As we put CH on the surface through dissociation of methane and then introduce the oxygen, this is the time pulse in seconds of carbon dioxide, the big pulse, and water coming off the surface. You can see that the pulse shapes are quite different, the time dependencies are different, and each of these can be modeled. A modest rise in temperature from 425 to 450 Kelvin gives rise to the much shorter time scale of these pulses, and this is simply how we get activation barriers for the various surface processes occurring. So I won't go into the details of that. Let me just mention that we can also do mixed beam experiments. So finally I'm using the two beams, methane and oxygen, and under steady state conditions measuring the production of the various products indicated here. So you've got the dominant product at 1000 Kelvin is this carbon monoxide, and remember that what I'm saying is that at this temperature the carbon monoxide is coming off at 11,000 degrees Kelvin, and there's very, very little trapped carbon monoxide formed at these high temperatures. Here's the hydrogen product. We're still getting some CO2 and water production at 1,000 Kelvin. Okay, so the summary of this part is simply that we see that methane can adsorb by a direct activated channel, and the CH stretch mode assists in that process. We've also seen that there's a steering assisted process, but it's not of much use to catalytic chemists because you need to rotationally quench the molecule in order to get through that steering assisted process. I don't know how you would rotationally quench a methane molecule in one of your reactors. It needs to be down to a gas temperature of something like 50 Kelvin in order to get it over there. The products on the surface, as I've indicated, are those shown here. Methyl is stabilized, it's metastable, but stabilized at 150 Kelvin, and at higher temperature CH and then carbon, we get very rapid exchange with deuterium, and then we see these products in the gas phase that I've just been describing. Now, if I've got a few more minutes, 5. Good. I'd like to talk about something completely different. So rather than carrying on in detail with our results on the methane, and I think I could genuinely bore you with the amount of detail we have on this, let's just change the topic to a recent result that we've obtained, which may or may not have any relevance to Fischer-Tropsch processes. It happens that the result is obtained on a cobalt surface. So this is the title of this part of the talk, which we believe is of some interest. It's about to be published in JACS, and it's a piece of serendipity. We happened to find that there was a system that formed a very well-ordered structure, a co-adsorption system of CO plus potassium, and this enabled us to do a detailed analysis of both the structure and the electronics of that system. Now, just to place this in context, I'm sure you're all aware that if you co-adsorb potassium and carbon monoxide, there is an increase in the heat of absorption of the carbon monoxide. And these are our own calorimetry data, so this is for single crystal nickel 100. Heat of absorption on the clean surface, about 124 kilojoules per mole. When you pre-adsorb a small coverage of potassium, that initial heat of absorption goes up very substantially to 190 kilojoules per mole. When we published this in Nature back in 1992, we believed the current model, which was the model that Jens Loschkoff and others produced, which is that the influence of the potassium was to create an electric field. So this potassium ion here generates an electric field, and the CO molecule sitting in that electric field has its 2 pi star d mixed orbital state pushed down below the Fermi level as a result of that. So more charge flows into the 2 pi star state of the CO. So the CO becomes more negatively charged, first of all. Secondly, more strongly bound on the surface because this 2 pi star d mixed state produces most of the bonding. And thirdly, because it's an anti-bonding state with respect to CO, it means that it's weakened the CO bond and the molecule has a greater propensity to dissociate. Here I'm saying something that I'm sure you're all very familiar with. So now the question is, I'm going to ignore this statement here. Is this actually what is happening? What we wanted to do was find a system where we could determine to the nearest hundredth of an angstrom the structure of this system and then see if this model was correct. And we finally found a system, and it happened to be on cobalt, where you get an ordered structure. And we published this structure back in 1995, and I have to tell you that I told my research students that my reputation was at stake when I published this. I wasn't really that confident in the structure. We spent ages trying to check the data and finally decided there was nothing wrong with the data. So here you've got a plan view of the cobalt 10 bar 10 surface, top layer cobalt atoms, second layer cobalt atoms, the light and the dark blue. Red circles are potassium atoms, black dots are the CO molecules. The CO molecules standing upright on the surface. And from the plan view, nothing strange has happened. The potassium atoms occupy the sites they occupy without CO, which is this large hollow site here. The CO molecules would be on the bridge sites without potassium, and you see that they're pushed off the bridge sites slightly, and the CO molecule is also tilted by the presence of the potassium. But these are minor effects, nothing terribly surprising. What was surprising and disturbing was the fact that the potassium atom was found to have lifted off the surface. So the carbon monoxide molecules caused the potassium no longer to be intimately bonded to the cobalt, but to be lifted off the surface so that the center of the potassium was slightly above the center of the oxygen atom. That's what surprised me, and I had no intuitive understanding for that. And in fact, I think there was no model in the literature that gave us an intuitive understanding. Now, what I'm going to describe here are the results of our detailed density functional theory calculations. These are so-called slab calculations, and I'm sure you've come across these. We started this work back in 1990, and what we have found is that by benchmarking this work against our detailed crystallographic analysis and against our measurement of bond energies, we can improve the level of the calculations. So using gradient density corrections, this approach is now yielding structures that are in almost total agreement with experiments. So this is a totally first principles calculation. It does use an enormous amount of computing time. The structure I'm about to show you took something like 20,000 hours of CPU time to calculate. But it's a first principles calculation, so you're not putting any assumptions into that calculation. If I just can show you this as an example of a well-defined structure, this is what I referred to initially. If you absorb ethylene on platinum-111, it goes quantitatively to form epalidine at room temperature. So here's the epalidine species. Sommerjai and Van Hove published the structure using Lee, and what we found recently using density functional theory is that we get exactly the same structure they get. So by exactly the same, the small relaxation of these three metal atoms away from the surface is reproduced in the calculation, and all of these bond lengths are within experimental error of the experimental results. What is more challenging is to get the energy right, and you'll see that the experimental and calculated bond energies are each within the error margins of both. So we really are able to reproduce these things with some accuracy, and therefore we can have some confidence in the results. So here's the result of the calculation for potassium plus CO, and comparing the surface structure with the experimental surface structure. And you'll see here the key parameter that I was worried about, the potassium atom lifting off the surface, is reproduced by the theory. So here we've got a molecular dynamics program. We can start by putting the potassium atom intimately bonded to the cobalt, but all it does is lift up until the potassium center has lifted above the center of the carbon monoxide molecule. So now we have not only confirmed the experiment, but we have the ability to understand why that's happening. And you'll see why I think this is saying something a little bit new. Just to see the comparison in detail between experiment and theory, you'll see that the theory is a bit conservative about those bond lengths compared with the experiment, but I'm sure you would agree that the agreement here within a tenth of an angstrom is really not too bad. The details of the structure are reproduced to within that sort of accuracy. So now we can take apart the calculation state by state, or we can look at the total charge distribution, and we can also make very beautiful view graphs out of this. So when you've got research students who know how to do it, it's just great. So here we have the cross-section through the surface. First of all, in the top curve here, we've got a cross-section showing the charge density difference that occurs when you bring the potassium atom up to the surface. So we're looking at the charge density, first of all, without the potassium and then with the potassium present, just to see what happens to the charge flow around the carbon monoxide molecule. And what you can see here is
that the charge flow is very much dominated by a 2 pi star type state around the CO and D type states around the cobalt. If we now look at this in a three-dimensional plot, it becomes a lot clearer. So charge density increase as a result of putting the potassium atom is shown in red and decrease shown in green. And you can see immediately that the major effect of bringing that potassium up there is an enormous polarization of the CO molecule. So that the oxygen end of the molecule is now close to -1. And this end, the carbon end, is now close to +1. So the charge difference is not, the essential feature is not the flow of charge between metal and molecule, but it's the polarization of the molecule itself. There is a change in the total charge on the CO molecule, but that is a second order effect compared with the polarization. Now we can look at this eigenstate by eigenstate, and so here is the dominant bonding state. This is at gamma bar, so there are many of these states depending on the value of the wave vector. But just taking this highly symmetric state as an example, we see again the charge domination around the oxygen atom. So this is a highly distorted 2 pi star state, and